All right. Good afternoon. You're seeing this Tuesday afternoon or Wednesday. Today's Tuesday, right? Yep. Or Wednesday morning. And we just want to kind of take up these questions quickly. So, number one asks you to compare the rate of stellar evolution between high mass stars and low mass stars. Higher mass stars go through their evolution a lot more quickly. They go through it so much more quickly and they burn their fuel much more quickly. Right? Because there's more mass, there's more gravity. Right? So I think it was near the beginning here. Right? High mass stars burn their fuel at a much faster rate than smaller stars, resulting in a very fast evolutionary pathway. Right? With the stars spending less time on the main sequence and less time, right, in the post main sequences as well. Right? Large mass stars, there is more gravity. Because there's more gravity, there's more pressure, there's more heat. Okay, because there's more heat, the nuclear fusion can occur much more quickly. Contrast the movement of a large mass star on the HR diagram to that of a low mass star after they leave the main sequence. Okay, it was here in this diagram. Low mass stars, they ascend almost vertically into the red giant phase, right? Whereas larger mass stars, they move more horizontally across the HR diagram. Right, the large mass stars, right, they move horizontally. Small mass stars move up. Number 13, what is the helium flash found in small stars and what is the cause? Okay, so in the red giant phase in a small mass star, it becomes electron degenerate. So meaning electrons are freed up and it no longer responds to thermal pressure. So normally what would happen when a core gets hot, it would expand. So that heat is balanced out by the expansion, and the expansion allows the star to actually cool. So you have a balance between temperature and expansion. As the star gets hot, it expands, but that expansion releases some of that heat. In the degenerate core of a small mass star, when the helium core starts getting hot, right, it doesn't expand thermally. It doesn't balance out the heat. The degenerate core doesn't doesn't expand as the helium core gets hotter and hotter, right? So what we have is this core staying the same way. There's no way to bleed off that heat, and because we can't bleed off the heat, the core gets hotter and hotter and hotter, and we have a runaway nuclear reaction. We have the helium flash. Larger stars do not undergo the helium flash because their core at this point isn't as dense. Because it's not as dense, there's not as much degenerate electrons, right? So because there's less electron degeneracy, the helium core in a high mass star can expand as it gets hotter, right? So it doesn't have, and because it can expand as it gets hotter, right? It doesn't have that abnormal buildup of heat. It doesn't have that runaway nuclear fusion in the helium core. So we don't have the helium flash. Number 4, explain the process of the fusion of elements in large mass stars, including the sequence. So let's go back here. So, large mass star, at the very beginning, helium, and we have, hydrogen, we have hydrogen fusion. The hydrogen fuses into helium, right? And then the core collapses and it gets hotter and hotter and hotter, and it starts fusing the helium into carbon. The carbon core, right, fuses carbon into oxygen and so on. So actually, let me rephrase that. The hydrogen core fuses into helium. The helium core collapses, gets hot, starts fusion of carbon, right? So that helium fuses into carbon. The carbon core then collapses, gets even hotter, starts fusing into oxygen, into neon, magnesium, silicon, and iron. Okay, So each time the core runs out of its fuel, whether runs out of hydrogen, it collapses, heats up, and starts fusing that helium. Okay, then the helium core, right? The helium core starts to fuse into carbon. Okay, so then we have carbon left over in the core, right? Nuclear fusion ceases because it's not hot enough. Gravity compresses the carbon core. It gets super hot and starts fusing carbon into oxygen. Right? And when all the carbon is used up, you're left with the oxygen core, right? It's not hot enough. It collapses due to gravity, right? Gets hot and starts fusing into neon, and so on and so on and so on until we hit magnesium, silicon, and iron. Why does it stop at iron? Okay, if we look at the mass per nuclear particle, okay, hydrogen into helium, right, into carbon, into oxygen, what do we see? We see that their mass starts decreasing. Okay, their mass decreases. So based on Einstein's equation, energy is equal to mc squared. If their mass is decreasing, that decrease in mass is made up for in energy, and that energy is what radiates out. Once we hit iron, right, after iron combining nuclei fuse, right, the mass starts to increase. Okay, we start increasing in mass. So if mass increases, that means that the energy starts to decrease. The amount of available energy to radiate out decreases. Remember, it's an equilibrium, right? They're equal. Energy and mass are equal, but if mass starts to go up, that means that there's less energy available. So once the iron forms in the core can no longer emit energy, and the core can never reignite. The star is done. So an iron core, if it was to fuse, it would be absorbing energy. Right? Stars give off energy. They give off light. They give off all the radiation. An iron core star, right, cannot burn, cannot go through fusion, because to fuse iron, you need to absorb energy instead of releasing it. Okay, what happens to the iron core after fusion stops? Okay. Gravity collapses the core, gets hotter and hotter and hotter and hotter. Then we get photodisintegration. Right? It's so hot that the radiation has so much energy, it breaks apart all the atoms. Right? The atoms are broken down into their subatomic particles. Right? So let's go back here. Right? So let's get back. So photodisintegration, nuclear fusion, photodisintegration undoes the nuclear fusion and absorbs a bunch of energy. Okay, in doing so, the core gets cooler even more, reduces pressure outwards, so the core keeps collapsing even faster. Right? So now the core doesn't have any atoms in it. The core is all subatomic particles, electrons, protons, neutrons, and photons or light. Extremely dense. Right? It's so dense it starts crushing all the particles together. Right? Protons and electrons get crushed up. Okay, so the protons and electrons, they get crushed to form neutrons and neutrinos. Okay, so the protons and electrons, I think I said photons yesterday. That's incorrect. If I said photons, I have a feeling I did. I'm pretty sure I did. I was very tired. Okay, the protons and electrons are squeezed together, forming neutrons and neutrinos. Thing is, with the neutrinos, they will escape the core. They will take energy with them, cooling the core even more. So as the core gets cooler, less thermal pressure outwards, the core collapses even more. So that iron core is no longer iron, it's all neutrons and neutrinos, right? And it just collapses and collapses and collapses to a point where it can't be compressed anymore. The neutrons cannot be compressed any further. Okay? So we go beyond electron degeneracy. We collapse further beyond that, right? Because there's no electrons to resist the pressure. The neutrons are collapsed to the point where the matter actually comes in contact with each other. It's extremely dense, right? But they can't go any further, so it's kind of rebounds outwards like an elastic ball. And this outward rebound is very explosive. It blows away the non-burning outer shell of the star, and it blows away all the, the silicon and the neon and the oxygen and the helium and the carbon. It blows away all those shells, scattering what's left of the star to the cosmos. Okay. 7. What type of star produces a type 1 supernova, and what type of star produces a type 2 supernova? Type 1 supernova is a white dwarf star. Right? So this is kind of answering number 8 as well. A white dwarf star, if it is in a binary pair where there's two stars orbiting each other, we have a white dwarf star and a normal star, let's say main sequence. The white dwarf star's gravity is going to pull some of the gas off of that main sequence star. And that gas and matter is going to accrete around the white dwarf. And if it reaches the Chandrasekhar limit, right, of 1.4 solar masses, right, we go back here, right, if we reach the 1.4 solar masses, right, this causes it's so massive now at this point that white dwarf will collapse even further. Right? The white dwarf collapses, it gets hotter and hotter, and it gets so hot that it fuses carbon. But because that white dwarf star was carbon everywhere, so that chunk of white dwarf, it's all carbon, and it all collapses and it gets hot all over at the same point, the entire star, the entire whatever's left, undergoes nuclear fusion at the exact same time, and it causes that star to explode, and we have our type 1 supernova. Type 2 supernovas happen from supermassive stars, right? Or just massive stars, even supermassive stars, where you end up fusing to the iron core. The iron core does not release any energy anymore. So the core cools down, the core collapses even further. We get the photodisintegration. We get the presence of neutrons and neutrinos. Neutrinos bleed away some of the energy, and the core collapses as far as it can. Then it rebounds outwards, exploding the star. Number 9, what conditions would have to change for our sun to ever experience a type 1 carbon detonation supernova? Our star would need to be part of a binary pair. It would have to have a partner. Two stars orbiting each other. And when our star would become a white dwarf, it would have to pull the matter off of that binary partner, reaching the Chandrasekhar limit of 1.4 solar masses, right? Collapse even further, carbon fusion all throughout the star, exploding the white dwarf. Okay, that's those questions. If they don't make sense, right, please reach out to me. I'm just going to pause it and then get ready for the next lecture. So give me a moment. Okay, so let's resume here. Okay, we've taken up those questions. We left off at the collapse of a massive star, right? So what's left in the core, right? The carbon core starts to collapse. We get lots of heat, photodisintegration, right? So the protons, electrons all fuse, forming neutrons and neutrinos. The neutrinos escape away, taking some of the energy, and what we're left with is neutrons. And the neutrons the gravity pulls them in as tight as possible until the matter actually collides with each other. And this is a strange concept, right? If you're watching my hands touch together, or you put your hands together, you feel like they're actually touching. But the truth is, they're not, right? If you look at an atom, the amount of space that's actually within an atom compared to how much matter there is actually gigantic. Most atoms are mostly empty space. There's just repulsive forces, right? Opposite charges attract and like charges repel. The like charges are repelling, right? So when my hands are touching each other, there's nothing really touching. Right? It's a weird kind of concept, but atoms are there's so much space between the protons and the nucleus and the electrons. There's so much empty space there that the atom is mostly empty space. So when the carbon core collapsed, it collapsed to the point where the subatomic particles were actually touching each other. And then it exploded outwards, creating your supernova. But you have a remnant left behind, this remnant that is all neutrons. Right? So the remnants of a massive star are the neutron stars. And supermassive stars, right? There's so much gravity that they reach the black hole phase, and we'll get to that. So, what remains after a supernova? After a type 1, right, the carbon detonation, essentially nothing remains, right? The entire carbon white dwarf explodes, and there's just dust left behind. After a type 2 supernova, so we get a implosion of the core, then rebounding outwards. Okay, what's left is very, very small, very, very dense, full of neutrons, and it is the neutron star. Let's move me up here. So neutron stars, extremely small, but extraordinarily massive, meaning they have tremendous mass. They're extremely dense, and matter is so tightly packed, okay, in that sphere that they are so incredibly dense. So a neutron star is roughly 20 kilometers across the sphere. So that's not very big compared to what a star would be, right? Just a tiny amount of matter left behind in terms of size. But the average density, 10 to the 18 kilograms per meter cubed. Right? So think of the number 10 and add 18 zeros behind it. Right? So, and remember, 6 zeros would be a million. So 10 million, million, million kilograms per meter cubed. Right? So per a space like the size of this window you're looking at that I'm in, right? That would roughly weigh 10 million, million, million kilograms, right? In this kind of cube that I am existing in this moment in your screen. So here, a thimbleful would weigh as much as a mountain. So a tiny amount would weigh as much as a mountain. That is incredible. Okay, neutron degeneracy pressure supports the neutron star and prevents further collapse. So what essentially that means is that there is some repulsive force between the neutrons, right? They are resisting each other to a point. Okay, supermassive stars, the gravity is so strong it overcomes the neutron degeneracy pressure. But right now, where we're at in a neutron star, there's enough resistance between the neutrons that they can't collapse any further. Okay? And what we know about neutron stars is they're spinning super fast, many times per second, very fast, and they have very strong magnetic fields. Right? So essentially, if we read here, the original magnetic fields of the progenitor star, the star that came before it, those are all condensed into this tiny neutron star, so they are amplified as the core collapses. So these magnetic field lines are compressed closer and closer, right? So they become much more intense. So pulsars. A pulsar is a rapidly spinning neutron star that has these beams of radiation coming out of the poles. So a neutron star is spinning, think like a lighthouse, and out of the poles of the neutron star are these beams of radiation. So, right, we've got how can I best explain this? Let me see let me grab my phone. I'll be right back. Okay. I'm just trying to think of ways to illustrate this. It's not that easy. Let me turn on my flashlight. I want it turned on. Okay. So my phone represents a neutron star. It's not a great representation, but there's a beam of radiation coming out of the pole of the neutron star. So let's say this is the pole of this tiny, well, it's not tiny, but compared to a star, this 20-kilometer sphere. And it's spinning. Okay? So from if the beam of radiation is pointed towards the Earth, as it spins, we lose the beam. Okay? So it's spinning, but this is where this example's failing. There should be another flashlight on this side, right? That should be shining at you. And then it spins and it comes back and it spins. We don't see the beam. Then there'd be a beam coming out of this side and it spins, right? But it's spinning many times per second and I can't spin it quick enough and I'd end up, dropping my phone. But what we see, I don't even know if that worked for you, but what we see from Earth is we get these pulses of radiation. Okay, as the neutron star is spinning, right? So let's right. I got this little styrofoam ball here. I'm going to get this highlighter, kind of doing things on the spot. So, is the pink showing up? It is not showing up. Need a different color. Need something darker. Bear with me. That's not dark. All right, I gotta go get a marker. Okay. Let's hopefully this will show up because it's darker. Okay, that's showing up. Good. Good. So if the neutron star is arranged so that its poles are facing the Earth, right? So that's the pole, and that blue spot is where radiation is spewing out this beam of intense radiation. And as it spins, right, we don't get any radiation, and then we get another flash from the other pole, and then it spins, and then radiation, no radiation, radiation, no radiation, radiation, no radiation, radiation, no radiation. So it's spinning, and we get these flashes of radiation. That's the pulsar. We call those a pulsar. So a pulsar is a rapidly spinning neutron star that has a mechanism to beam radiation. So these beams of radiation are coming out of the North and South Pole, and it looks like a lighthouse, essentially. We've got these beams of radiation coming towards us. We don't quite understand what causes it, right? Like, there's no neutron stars nearby for humanity to study. Right? We can just see them in outer space with our most powerful telescopes, and we can see and detect the pulsing of the radiation. Okay? Some pulse periods are extremely stable, making them the most accurate clocks in the universe. Okay? So some of them are spinning at with such regularity that we can tell time with the pulses. It's so accurate. So the lighthouse model, you've got two hot spots at the poles of the magnetosphere. So that is the magnetic field surrounding the neutron star, right? So these hot spots in the magnetosphere charge particles to extremely high energies so that they give off radiation. And as the star spins, right, beams of radiation sweep outward like a lighthouse. So this diagram here is showing us a neutron star. Okay? And it's rotating on its axis. Right? So its axis is here, but the poles, right? We've got these beams of radiation coming out. This would be the magnetic north and the magnetic south. And we've got these beams of radiation being spewed outward. Okay, so these beams of radiation spewing outwards we can see, and it creates a flash or a pulse. Okay. Pulsars have been associated with the remnants of supernova. Here we can see the blown off shell of a star that exploded outwards, but at the core, there's a remnant. One of these is a star in the background, and the other is the pulsar. If you look at these photographs, they were taken over time. Right? You see one object, one object, one object. Oh, blip. We see a second. One object, a second. One object, a second. One object, a second. Still picking it up. One object. We can see the second. We can see the second. Right? We can see it appearing and disappearing, appearing and disappearing. Right? So it's a pulsar. It's following the lighthouse model. It's spinning, and because of its spin, sometimes we get a flash, sometimes we don't. Then we get a flash, and then we don't. Then a flash, and we don't. A flash, and we don't. Okay? That's what this image, and I'm pointing to the screen like you guys can see it. That's what this image here is showing. At the core of this supernova, right? This is the gas cloud that was blown away, right? The non-burning hydrogen, and then the shells of, the shells of, hydrogen, helium, oxygen, carbon, neon, silicon, right? Those shells all blown outwards. And what's at the center was the iron core that collapsed, photodisintegrated into neutrons. Okay, here is the Crab Nebula. Right, the Crab Nebula was a star that went supernova, and at the center, right, this is zoomed in at the center, right, the very center of the Crab Nebula, we've got our pulsar. Okay, so we've seen neutron stars at the center of nebula. The nebula are the gas clouds that remain after a star went nova. So neutron stars and pulsars, they are generally considered to be one and the same, right? So all pulsars are neutron stars, but not all neutron stars are observed as pulsars. First, reason why. The rotation in the magnetic field diminishes over time. So they're spinning, right, super fast, but over time they slow down. The spins slows, right? the magnetic field diminishes, right, to a point where they almost stop after tens of millions of years, so that they kind of come to a standstill and you're no longer getting the pulsing, right? The other thing that when some neutron stars, we can't see them pulse because the way they're angled, right? This one's angled so the beam's pointing at the camera, right? But if it was angled in a different direction, let me see how best to orientate this. Right? If it was angled in a certain way, the way that it would spin, right? So it's angled this way, right? And it's spinning. So I'm trying to watch the camera while I'm spinning it, right? The way it's spinning, the beams, I got to try and keep it still, right? The beams are pointing up and down. They're not pointing towards the camera. So it's still a pulsar, but not to us. We can't see the radiation beam. So that's number two, the vantage point. If the Earth isn't in the path of the beam, we will not observe the pulsing behavior. Okay, key ideas. Every high mass star, the iron core will collapse and you get a supernova. Most supernova, meaning a type 2, not a type 1 detonation, will leave a neutron star behind. Okay? Very, very massive stars, the gravity might be so strong that the neutron star will collapse even further into a black hole. But massive stars will leave behind a neutron star. And all young neutron stars are spinning and giving off radiation. Tens of millions of years, the magnetic field decreases, the spin slows down, and they may stop emitting the pulsing that we see. Okay, so that ends the discussion on massive stars. Tomorrow we are going to go into supermassive stars, and the supermassive stars, when they collapse, they go beyond the neutron star and they become the black hole.